Good afternoon. I hope you enjoyed your lunch. I'm David Kring from the LPI in Houston, and as Brad says, I'm going to be hosting Age, Dating, and Impact Processes number 2, Basins and Impact Processes. It seems like a redundant title there, Brad. Oh, okay. All right. Well, our first speaker is going to be Debra Needham. She is going to speak about exploring, someplace on the moon.
All right. We had a very interesting discussion in the last talk, or last session, about generically where we would want to go to figure out age dates on the surface of the moon. For crater chronology and basin chronology. And I'm going to talk a little bit more in detail about one of those very high priority sites in Orientale. Because we had such a great background, I'm not going to discuss all of the background of Orientale and why it's important, but I do want to recall that it is the youngest of the large lunar basins, and it's located on the western limb of the moon. So when you're looking at the moon, we'd basically be the wall over there looking at the moon. That's our normal perspective of the moon. So now we're looking at the western limb, and Orientale is this very large multi-ring basin that many of us know and love very much. So it formed about 3.68 billion years ago, but that date is from crater size frequency distribution, so we don't have samples from Orientale to actually know the specific age of this basin when it actually formed. And that's a very important basin to date, as David talked about earlier today, because it marks the end of the basin-forming epoch. And whether or not that marked a late heavy bombardment period, a lunar cataclysm, intense basin-forming period where there were a lot of basins forming over a short period of time, or just one of the last basins to form, that's part of what we want to go and figure out. And marking the end of that basin-forming epoch is very important. Also, like we said earlier, it's the youngest basin, so it's not going to be overprinted from Imbrium, so we can be sure that we are dating Orientale material when we go and pick up samples from Orientale. Okay, and then further, one more point is that it's located on the transition from the thin near side, so thin lunar crust on the near side, to the thick lunar crust on the far side. So the blues on the near side that face us is very thin crust relative to the far side, which has very, very thick crust. So going to collect samples from this transition area can give us some interesting insight into the geologic processes that were happening on the moon. Okay, so Orientale has 3 concentric rings. It's a multi-ring basin. The inner Rook ring is the innermost ring, the outer Rook ring, and then the Cordillera ring is actually outside the transient crater of the basin. Furthermore, it has 23 Mare ponds in addition to the very large Mare pond in the middle, Mare Orientale. And that shows up very nicely in this Moon Mineralogy Mapper color composite that highlights the mafic minerals. So the yellows and the oranges are popping out at you as mafic materials, and that's Mare basalts, whereas all the blue is mostly very mature material that's really been worked over and is a little bit spectrally more neutral. And the largest of these ponds, and the dates of these ponds have also been specifically analyzed by Jenny Whitten, who will talk later in the session about a companion site that I'll talk about in a second. But it looks like the ages of these Mare units get younger as you get farther outside the basin. And so going to sample at least one of these can help us understand a little bit more about the processes that cause volcanic activity to progressively go outward from the basin interior. Okay, so Lacus Veris is the largest of these Mare ponds outside of Orientale, and it's nested between the outer Rook ring and the Maunder Formation. And the Maunder Formation is what we think of as, or is interpreted to be primary Orientale impact melt. So that's impact melt, not ejecta, but impact melt, and sampling that material can get us the direct age of the Orientale impact, and that's one of the primary goals for going to this site. Okay, so like I said, Jenny Whitten will be giving a talk late at the tail end of the session on a proposed companion site to the one that I'm going to be talking about. So I'm talking about Lacus Veris, which is on the eastern side of the basin, closer to the thin crust side of the basin, and the companion site that she'll talk about is on the thicker side, and she'll talk about that later. Okay. So this is the landing site area that I'm proposing. It's an interesting place because it gives us access to samples from the Outer Rook Mountains up on the northern part, the Maunder Formation, which is in the middle, and then the Lacus Veris Mare Pond on the southwest. In addition, there's a sinuous rill that goes through all three of these units, and as many of you know, sinuous rills are very near and dear to my heart. They are ancient lava rivers, basically on the moon, that carved into these different units. So I'm really interested in better understanding how those features formed in relation to the Mare basalts. Okay, so what science can we address at this site? I list 3 science objectives, and I've tried to trace those back to the goals that we've talked about in this this NRC 2007 report, or the SCEM report. And basically, these aren't in priority order, they're more in accessed order in a traverse that I'll talk about in just a moment, but I think they're all very high priority science objectives in my opinion. So the first one is to determine the composition and age of the volcanic activity and investigate the sinuous rill formation. So we'll go to the Mare basalts in Lacus Veris down here and take samples there. And this addresses goals 5, which is talking about the diversity of volcanic materials that we can see in this area, as well as 7, which is the regolith, because everything's covered in regolith, so we'll learn something about regolith by sampling it pretty much anywhere. The second objective is to determine the composition and age of the Maunder Formation impact melt, so that's going into the middle unit of this kind of rough, hummocky unit. And that's going to address goal 1, which is looking at the age of Orientale relative to the bombardment history of the moon. The third goal, which is looking at the diversity of crustal rocks, so we're sampling a new part of the moon by going to this location. Number 6, investigating impact processes, and then again 7 is regolith. And then finally, the third major science objective to tackle here is determining the composition and depth of the Outer Rook Mountains. And this is really important also for crater and basin formation processes, because which is goal 6, because we're pretty sure we know how these things formed. There's been recent work drilling into the Chicxulub Basin that David Kring's been heavily involved with, and some of the results coming out of that are going to help really pin down how these central peaks form in these multi-ring basins. But whether they're excavated crust coming from deep or some sort of rebound process, which is less likely in my personal opinion. I think it's excavated crust. But we can go there and figure that out for sure. Okay, so how do we get to these places? So I'm proposing a traverse. This would be for farther down in the future of lunar surface exploration, but any one of the 6 stations that I've identified along the traverse would also represent areas where you could just go and land and tackle one or several of the science objectives that I've listed. So any one of these stations could be standalone landing sites. Station 1, so the landing site would be in the nice smooth Mare plains. And before I go into, because I have pictures of these, but so this would also traverse the different units. So this is another moon mineralogy mapper color composite image. So again, the reds and the oranges are the Mare basalts, the blues are mature material, and then within the Outer Rook ring, or Outer Rook mountains up here, you can see some purpley patches, and that coincides with some boulders and some outcrops of excavated material, so we can go and sample those to get actual samples of the Outer Rook mountains themselves when those boulders roll down the hill, so I'll show you those in a second. Okay, and then the slope map. Most of the slopes that I'm traversing over are very low. Obviously, there are some very high slopes that we would avoid, but it's a relatively traversable location as long as you pick your traverse carefully. Okay, So let's go into the landing site. So this is the landing site itself. It's relatively smooth, benign area. There's certainly lots of craters. I don't have a scale bar on this, and I apologize for that, but it's about a couple kilometers across. There's the tail end of the sinuous rill over on the right side of this image, but we can go over to the left, and with a 100-meter landing ellipse, you should be able to get here pretty easily. And then there are some fresh craters that you can go. These really small, bright spots are fresh craters excavating fresh material that you can go sample and get fresh Mare material that's been newly excavated. Okay, so going up to Station 2, this is a little hard to see, and I probably should have outlined this for you, but I will attempt to do this with this. There is a slight albedo difference, and I'm kind of tracing it. The Mare is down here, is this slightly darker unit, and then the brighter unit up on the top is the Maunder Formation. And traversing to this or landing near this contact would be very interesting to see geologic relations between these two units and to sample both of them if possible. Okay, let's go to the next one. So Station 3, now we're going up completely within the Maunder Formation, and again, there's some fresh craters to look at some of this Maunder Formation material and get a specific age of this impact melt material so that we can actually date get the age of the Orientale Basin impact event. Okay, so now 4, we're getting up right next to the sinuous rill, which is a very pretty structure actually, but I'm only showing you a little part of it so you don't get the full impact of it. But there are fresh craters very close to the rill, and if we can get... Oh, sorry, thank you. Yeah, I've got my back to him on purpose. Thanks, David. So if I would like to look at whether there's any Mare material that came out of this rill, or if it's Maunder material all the way up to the rill, and that has implications for how the rill formed, whether it was a surface channel that was overflowing its banks with lava, or if it was just carving within the Maunder Formation impact melt. So that's of interest to me and other people too as well. All right, and then up to 5 is the last one I'll zoom in on. And again, this is a kind of a hard contact to see, but I'll try to trace it again. So again, we've got a slightly darker Maunder Formation on the south here, and then these boulders are up in the Outer Rook Ring Mountains. And so these boulders, some of them have come down. There's some very faint boulder tracks that come down and end in boulders at the bottom of the slope that we could access directly and get samples of. Okay, and get the age of, and the composition of the Outer Rook Mountains, and potentially figure out the depth that it originated if we get the chemistry in enough detail. Okay, so now I basically go through and I'm trying to fill out the science traceability matrix with identifying the specific measurements that we want and examples of instruments we'd want. And basically they're pretty much the same across all 3 sites, so I won't spend too much time on it because I'm running out of time. But basically we want to measure the bulk and trace element compositions of the basalt to address science objective 1, as well as measure relative abundances of geochronometers to get the ages. And so we've talked about we'd want a stereo camera and a micro imager for navigation and context images, and then an XRF XRD or a mini SEM, which is under development right now, to get the chemistry. And then we've heard from Barbara's surrogate Noah about Carly with a LIBS laser-induced breakdown system, or spectrometer. So this is and this is basically the same with the added caveat that we could use the micro imager to look for shock features in an orthosite for the impact-related objectives. Okay, and then this is my summary slide, and I'll leave it here, but this is basically just everything that I just said in a tabular format, and with a couple additional potential instruments that we might want, like a UV-Vis spectrometer to assist in identifying samples for the analysis themselves, and then we would need some way to retrieve samples from the surface and put it on the instrument deck, whether that be a rover or a lander. And with that, I will stop and take any questions. We have 2 minutes for questions or comments. That's fine. You might have more comments or questions after Jenny gives her talk too.
Are you going to the microphone? All right.
Okay.
So my one question is, if I look at lava flows like in Hawaii, they fan back and forth and then cover a wide area. But if I'm looking at the rills, they make funny turns.
Yes.
And seem to be all concentrated in like one riverbed. Any explanation for that?
Sure, and lava flows do this in Hawaii as well. They concentrate, so when you have a sheet flow, it's a really broad lava flow that cools from the edges, and then the fastest, hottest part of the flow is moving in a channel in the middle. Often, it doesn't always. If there's enough lava going through it, it will form this channel in the middle of it. But yeah, it takes a lot of lava, and then the sinuosity is, that's weird. We think it's just because parts of the lava flow get cooler, and then it forms a temperature gradient laterally as well as horizontally or vertically through the flow. And if you're moving faster, it'll bend around it. But that is really people don't know why rivers meander on Earth either. So it's kind of a really fine scale properties of the subsurface, maybe. But it's an open question.
One more question, Chip.
Yep, just actually 2 comments, and I'll make them really quick. One, what you may want to do, rather than do individual chronometers, potassium, argon, rubidium, strontium, neodymium, samarium, or uranium, lead, you probably want to do all of them, because all of them could be potentially reset by their thermal history. The other thing is, making that point, is, we've had an awful lot of talks on age dating lunar surfaces. But yet, I'm not sure we have the infrastructure to do all of this. And I don't think we have enough chronologists involved in these sorts of discussions. For example, I'm just curious, how many people who do chronology are here? Just raise your hand.
There are a couple. And Barbara's here in spirit.
And Barbara is, but she doesn't have a lab right now, right?
Well, it's getting set up. I mean, she certainly has one.
But anyways, my point is, we need to have more chronologists involved in these discussions.
Sure.
And maybe a little bit bigger infrastructure.
Yes, absolutely. And Barbara, I mean, for example, Barbara's working on miniaturizing the capability of taking this to the moon. It is potassium argon.
I was more talking about once the samples come back.
Right, so exactly. So this particular concept is not sample return. It's just in situ science. Absolutely, for bringing samples home, we need more. And I know we have colleagues in Australia and all over the globe who are helping in that story.
Okay.
They're not necessarily here, but I know they're here in spirit.
Okay, thanks.
All right. Thank you very much, Debra. Okay, so I know there is at least one other question, Debra. Just remind that if all goes well, Brad is going to have time for a little discussion period with a panel up here, so you can hold on to your question. We'll come back, have time hopefully to come back to it. With no further ado, we would not be able to function without Ricky Guest. Thank you, Ricky. Okay, so without any further ado, I want to introduce Jim Head, who is going to speak about Orientale Basin. Jim.
Okay, thank you very much, David. I really want to talk to you today about a human robotic exploration design reference campaign, architecture. So the question here is, we've heard a lot about all detailed, specific missions and types of things that we can do, and there's a cornucopia of just a gold mine of things that we could do individually. But what I want to talk to you today about is how we can integrate that so that we, in fact, are able to tackle huge problems with the same kind of capabilities we've been talking about commercially as well as internationally. So the idea here is to focus on opportunities related to one of the most fundamental aspects that you've heard about today from Debra and many others, and David, et cetera, the Orientale Basin. And the idea is to wrap an architecture around the concepts and then think about how individual nations and how individual commercial entities could actually contribute to that endeavor. And so, for example, virtually any country or any individual who can find the money to actually get payloads onto missions and our commercial partners could contribute to this larger question, this larger architecture that really would help us to get some fundamental information in an additive and a kind of a synergistic sense. So why do I have humans? Why not just robotics? Well, in fact, of course, we learned yesterday from Jack Schmidt his really elegant talk about the characteristics of the Apollo 17 Taurus Littrow site. If you did not understand from Jack's talk why humans are essential in doing field work on the moon and why every crew ought to have at least 2 scientists, hopefully geology, geophysics oriented, to explore the moon, then you were asleep, okay? I mean, it's just amazing. Think about every station Jack talked about, the questions he had when he picked up the samples, the selection process he went through as a human being, and you know, with an intellectual interest in the outcome, et cetera, and the speed with which he was able to do that, and how he was able to, in fact, integrate his findings immediately and to go on to the next station even better educated with the results from the previous one, and then persist when he came back over 40-some years to try to get the answers to these things, learning new things every time. So humans are absolutely essential. We know where to go on the moon based on the data sets we have. You know, we can learn even more from robotic missions, but in fact we can also do them in tandem and together, and that's what this architecture, this international architecture, is all about. And it has tremendous capabilities for humans as well as for commercial entities. So let me talk a little bit about this. So you're seeing here the results of the 6 Apollo scientific expeditions to the moon, absolutely amazing results that form the basis for the cornerstone for solar system science. I mean, that is what the moon is. So if we take a look at the characteristics of these things, then we know that the moon is, in fact, really fundamental in our understanding of basic questions about solar system science. We ask questions of the moon that are brought up by our findings on the moon, Mars, Venus, Mercury, and we can actually go to the moon to establish these answers. In fact, if we think about it, the coordinated human robotic exploration is important, is many, many fold. So we're going to talk about that first, and then take a look at the range of approaches and architectural elements that we would have in this type of approach, which optimizes, you know, the capability to answer these huge questions. So this is the 6 types of missions that make up this fundamental architecture. First of all, there's precursor missions. What do we need to know before we send humans, okay? So, you know, you may know that before the first Apollo astronaut set foot on the moon, Neil Armstrong, we in fact had sent 21 robotic spacecraft to the moon. The United States alone had sent 21. The Soviets had sent many, many additional ones as well. So we need to know what is there before we send humans. Precursor missions, which are the kinds of things we've been talking about a lot today, would be very, very essential part of this architecture. The second is context. What are the robotic mission requirements for final landing site selection and regional context for landing site results? You know, we might send several missions, of course, to try to optimize where we go with the human exploration. What about infrastructure and operations? What specific robotic capabilities are required to optimize human scientific exploration performance? People don't think about this very much, but in Apollo, the Lunar rover is a good example of a specific robotic capability that optimized human scientific exploration performance. Just listened to Jack yesterday about the range of areas they were able to go to, things they were able to do, and to optimize getting to different places in the human exploration traverses and missions. Interpolation. How do we use robotic missions to interpolate between human traverses? So, for example, if we're exploring the Orientale Basin, we're not just going to go to one place, we're going to go to many places over years. And how do we use robotic missions to interpolate between traverses? And I'll come back to that in a second, because in Apollo, we actually did some of that, or at least planned to do some of that. Extrapolation. How do we use robotic missions to extrapolate beyond the human exploration radius? In Apollo, it was about 7 to 7.5 kilometer radius was the walk-back constraint. And so, you know, there are other constraints that will happen about the length of traverses and the distance you can get away from your home base. So how do we use robotic missions to extrapolate beyond that? And finally, progeny. What types of targeted robotic missions, successor missions, might be sent to the region to follow up on discoveries during exploration and from post-campaign analysis, just like Jack was talking about? We did not, in fact, pick the landing site specifically landing site until we had gotten the results back from the previous Apollo mission, so we could integrate these new discoveries into the best possible landing site for that particular mission. Same kind of thing is going on there. So let's take a quick look at a series of traverses and get some kind of lay of the land, how these different types of mission options might be able to be utilized. What this map is a series of circles, 1 kilometer each, ranging out to about 14 kilometers, and the central point here is the central point of each of the Apollo missions, or at least one end of one of the Apollo missions. And you can see here that actually, like Apollo 17, got out to a total range, end to end, of an excess of 11 kilometers. That's not the traverse distance, that's the range over which, lateral range over which they were able to go. So that's pretty impressive. You can see Apollo 16, 15, and also you can see the robotic missions. For example, Lunar 2 got out to close to 14 kilometers, and you can also see total distance for discovery and opportunity in that same context. So this really illustrates the kinds of things you could do to complement and implement and supplement, interpolate and extrapolate using robotic missions in concert with human missions. And interestingly enough, part of my job in working in the Apollo program was, in fact, working on Apollo 19, 20, and 21, which nobody has ever heard of, I'm sure. Maybe you have, but anyway, they were going to the moon. And one of the things that we were planning to do was, in fact, to take the rover after the astronauts left, hook up, before they left, and hook up a dual-mode structure which would take experiments and then traverse all the way to the next landing site, doing remote sensing and observations and making measurements to interpolate between the landing site that just deployed this rover and the one that was going to be landed on in a few months. So this is not a new concept, but it's an incredibly important one. We spent a lot of time trying to think about how selection of landing sites could be optimized to make long-scale gravity, all sorts of measurements, traverse geophysics, et cetera, in between these different landing sites. So this can be absolutely utilized in the context of the missions to Orientale. Well, why Orientale? We've got an architecture, we've got a lot of options here. Why Orientale multi-ring basin? Well, it's clear that the question of the origin of the crust that we talked about earlier today is really important. Not only the primary crust, but the secondary crust as well. This is critically important because the moon is a laboratory for the study of primary and secondary crusts in early planetary history. We will never get, at least in my lifetime, the detail that we have for the moon, and so it's really informative for us to ask and answer these questions in a place we can have access to. The second thing is that when we do look at the lunar crust, we had a Microsymposium 56 which treated the crust of the moon, talked about it. Crust geometry, physical structure, chemistry, mineralogy, petrology, exogenic crustal modification by impact, such as Orientale, and chronology of crustal formation and evolution as well. These are all critically important points that we discussed and identified at the Microsymposium, and they form the basis of our discussion of using Orientale. Of course, we want to understand how multi-ring basins form. What's the difference between the crater characteristics, their excavation, and the way the impact cratering process works over a range of diameters up to, in fact, through peak ring basins out to multi-ring basins. And of course, Orientale is the type area for lunar basin formation and evolution. It is essentially the youngest one, as was pointed out earlier, and indeed is one which has not been covered by extensive Maury deposits, filling up most of the rings and the interior melt sheet like most of the other impact basins. So we have exposed the three major basin characteristics, the rings, and then an interior ring as well. And we also have, in fact, the major basin deposits, the Igneous formation, the basin ejecta, Modest Rook, the knobby domical facies between that and the basin melt of the Maunder formation. Beautifully, beautifully exposed. So another thing we want to know is the composition of the ejecta from the Orientale basin. And I fear that, in fact, one item didn't come up here, but Caleb Fassett had a really good map of the detail of the thickness of the ejecta as a function of distance from the radial rim of the basin. And we know what the thickness more or less is, and we can go map that out as a function of what's coming out of the basin itself. And of course, looking at the characteristics of the massifs and the ejecta, we can piece together the structure and composition of the lunar crust. We can test the magma ocean model. We can test the regolith development model, etc. So this is a classic way that we can do it. And in fact, if we take a look at the mineralogy data that we have from M-cubed and other information, we know where to go. We have at places like the red dots shown on the lower left there are, in fact, 98% plagioclase in excess of that, Leah Cheek's work. So we know where to go. We just need to know the context of these deposits as well. And if we take a look again at the exposed Orientale impact melt sea, this is absolutely incredibly exposed, and James Cassanelli is going to talk about this in the next talk. But this is very controversial. Did it undergo extensive differentiation? Did it undergo equilibrium crystallization? How thick is it, et cetera? These are critical aspects of our understanding of the impact process, as well as the gravity structure of the basins, et cetera.
2 minutes,
And then,
Jim.
of course, we can. Okay, got it. We can link the Orientale Basin to the Apollo missions. Each of the Apollo missions sites were chosen based on understanding large-scale structure, like 17, 15. You can see are at the base of these major rings that are analogous to what we see in Orientale. So anything we learn from, in fact, the Orientale Basin and landing and studying these areas can be, in fact, related back to the sample collection we have and vice versa. And so you can see here that there's beautiful examples of things that we would want to follow up, collecting samples from Orientale and then linking them to Apollo. And of course, we've already heard from Debra, and we'll hear from Jenny Whitten in a moment about the Orientale lava flows. Jenny has shown that the range of ages in the basin is similar to what we see for the near side as a whole, but the magnitude is much lower, and we need to understand why that is the case. So finally, what about human robotic scientific destinations? We have 4 major regions of interest. I'll point out just briefly here. Region of interest, the origin of basin rings and crustal structure. Taking a look at the interior here, the outer Rook Ring, for example, understanding what's going on with this major apparent fault scarp there as the basin collapses. We also have the origin of the inner Rook Mountains. This is the peak ring part of it, but what is the peak ring? Debra pointed out Chicxulub is informing us about that, but here we don't have it covered by everything, but we can take a look at its relation to impact melt. The third one is, of course, the impact melt sea, and James will talk about that in a moment. Beautifully exposed for us to go explore. That's a major region of interest. And finally, we have this dark halo crater, which is an Ionian-like volcanic explosive eruption, which will really inform us about how pyroclastic emplacement works. So basically, the human robotic architecture is a basis for design reference missions, which we're working on as we speak from all the different opportunities, and we have range of features of types of missions, landed missions. So for the Land and Mission Workshop, commercial entities, as well as international cooperation, can really bring these things all together into a dedicated sense of trying to understand some fundamental problems. Thank you very much.
Perfect. Thank you, Jim. This paper is open for questions or discussion. Yes, sir.
Hello, I'm Mark Cohen. I was wondering if there's anything about the human missions specifically that go beyond sort of vague allusions to Apollo.
Well,
okay, thank
I'm
you.
not well, let me just say, you know, I think if you listen to, if you were able to listen to Jack Schmidt's talk yesterday, I think that you can see what humans can do in terms of, in fact, using logic, using observations, using professional training, like Jack had as a geologist.
Okay, what I'm asking is there anything of notion of, given your ambitions for the traverses and how long it takes to do traverses, how long would you like to have a crew on site or in the field there, and how many crew members? And
yes, absolutely. So we've been working with our colleagues at MIT, Jeff Hoffman, one of the shuttle astronauts. We've been having several classes in which we've been looking at ways in which we can optimize that. So yeah, we're talking about crews, minimum crew of 3 on the surface, and stay times for the sorties of 2 weeks, basically, of a lunar day. Okay, a lunar day. And that's the kind of thing we're operating on with a, you know, we worked out some traverses and also extended the distance by having kind of a lunar tent that can be utilized for astronaut rest during those days as well. So that's the kind of thing, that's the magnitude of the kind of thing we're thinking about initially.
all right, great, thank you.
Thank you very much, Jim. We'll go ahead and move on to the next presentation. This will be by James Cassanelli, who will speak about impact melt sheet composition, age, and igneous differentiation with a big question mark, commercial mission goals. James, are you online?
I am. Thank you. So I'll add to the discussion on the lunar impact basin melt sheets as targets for future landed science investigations, and outline some objectives to achieve at these important targets and why we might want to investigate them. So I'm going to begin by just talking about some of the scientific background and motivation for why we might want to visit these impact melt deposits, and then outline some currently outstanding unanswered questions regarding the nature and evolution of the lunar basin impact melt deposits, and then talk about how those might be addressed through some first-order landed science mission concepts. So we know from scaling laws that during the impact process, large volumes of target material undergo shock heating and melting, and the volume of this material is predicted to scale with the fourth power of the transient cavity diameter. The consequence of this prediction is that large basins will produce large volumes of melt. To give you a sense for what large means in that statement, I've got a figure here from Vaughn et al. 2013 showing the predicted volume of the Orientale melt sheet, which is about 10 to the 6 cubic kilometers, with some other perhaps more familiar things for reference. And this becomes particularly important when we consider the broader population of lunar basins, as there are many such large basins. The cumulative volume of melt that could be produced is something on the order of 5 volume percent of the lunar crust. As a result, lunar impact melt could have substantially contributed to compositional variations in the lunar crust through processes like igneous differentiation, and may in fact be represented in the lunar sample collection. Vaughn et al. Speculated that perhaps the young ferrite and orthosites could be actually differentiation products from impact melt. So it's clear from this and previous discussions that it's important to understand basin impact melt. But these are difficult deposits to study because they're old and degraded and obscured through later impact cratering and Mare volcanism. So we're left with the question, if we want to investigate these deposits, where should we go? And I think many would agree that Orientale is perhaps an ideal candidate for that, as Orientale is the youngest and most well-preserved basin, but also because it contains the Maunder Formation, which is an interpreted cooled remnant of the Orientale impact melt, which outcrops within predominantly within the outer Rook ring of Orientale Basin. The Maunder Formation, if we look closer, is shown here. It's characterized by this heavily cracked, fissured surface morphology. You could see, I don't have a pointer here, but outside the bounding scarp of the central depression there. So the Maunder Formation is composed of two separate facies, the smooth facies, which is generally contained within the central depression of Orientale Basin, which is interpreted to represent a pure impact melt, which then grades as you move away from the basin center into a rougher, corrugated facies that is interpreted to represent a clast or debris-rich melt. The interpretation then from the Maunder Formation is that after the impact process occurs and the melt is generated, it is collected in the final crater through the collapse of the transient cavity to produce this impact melt sheet or sea that lines the basin of the final crater. The evolution of this impact melt sheet was investigated for Orientale by Vaughn and others in 2013, in an attempt to distinguish whether or not it might undergo igneous differentiation, so whether or not you would end up with something on the right like a homogeneous impact melt sheet or one that is compositionally stratified, a differentiated impact melt sheet. Ultimately, they favored a differentiated impact melt sheet based on considerations from smaller scale differentiated impact melt sheet bodies on the Earth. This fundamental problem was revisited by myself and Jim Head a couple years ago, this from a more physical perspective, where we were considering the process of crystal settling, which is a main mechanism by which impact melts may undergo differentiation. We found, perhaps unsurprisingly, that this process is critically dependent on the size of crystals that are nucleated within the melt during cooling, and that at low crystal diameters, there isn't much settling that takes place, and so this might produce a more homogeneous impact melt sheet. Based on the typical size of crystals in the impact melt rocks of our current lunar sample suite, which is about 2 millimeters, we favored a homogeneous impact melt sheet, although with the caveat that this may not be representative of the broader impact melt crystal diameters. There are, of course, contrasting viewpoints, and I'll mention 2 of those. The first from Spudasol in 2014 investigated the Maunder formation through a remote sensing analysis and suggested instead that actually the Maunder formation represents a thin, undifferentiated impact melt sheet. And then yet another from Brandon Johnson and others in 2016 from this from the standpoint of a Schoch's physics code simulation of the formation of the Orientale Basin, in which case the impact melt is predicted to be generated predominantly within the mantle and to stay there, because during the collapse of the transient cavity, crustal material, which is partially melted, is predicted to flow over the top of the impact melt, covering it up. In this representation, the Maunder formation then is this less shocked, partially melted crustal material, and not the true, I suppose, impact melt from the event itself. So these different models leave us with essentially 3 end-member configurations for the Orientale impact melt sheet shown here. The first 2 I mentioned before, the homogeneous and differentiated impact melt sheets, and then the last from the Schoch physics code with impact melt generated and kind of maintained in the mantle. Recently, I've been looking into ways to potentially distinguish between these end-member models through the use of Grail gravity data. Interestingly, Orientale is a location on the moon of negative density gradients with depth. And at first glance, this is somewhat inconsistent with the differentiated impact melt sheet, except for the fact that, of course, Mare Orientale overlies the central depression of the basin, and so that could potentially be the reason that we're observing a negative density gradient. So it's not totally possible to rule that scenario out. I wanted to show some preliminary results from some further work I've been doing in forward gravity modeling of the various impact melt sheet configurations. So that's shown here. The figure on the bottom shows radial profiles of modeled gravity free air anomalies versus the observed Grail anomalies. So this is for the homogeneous melt sheet, and you can see there's a fairly large discrepancy toward the basin center where the impact melt sheet lies, so not generally consistent with the observed anomaly. Whereas the configuration predicted from the Schoch physics code, now shown here, provides a much better match, actually. So these are continuing analyses and don't definitively identify what the overall structure of the impact melt might be. So there is really a lot of science to be achieved through land and missions to the Orientale Basin melt, in particular the Maunder formation. And I think there's 2 important questions that we can address. The first is, what is the structure and distribution of the Orientale impact melt? And there are many smaller questions involved in there, such as, what is the nature of the Maunder formation facies? Is it actually impact melt, or is it this partially melted crustal material? Is Orientale impact melt exposed at the lunar surface in the Maunder formation, or perhaps maybe within ejecta of superposed craters like Maunder and Kopf? Is the Orientale impact melt instead contained at depth as predicted by the Schoch physics codes? And ultimately, what is its thickness and volume? And then the second important overarching question is, did the Orientale impact melt undergo igneous differentiation? And in the interest of time, I'll just skip over these smaller questions associated. So these important scientific questions can be, of course, addressed through a series of landed science missions, ranging from landers to rovers to sample return. And I'm going to discuss those briefly in a minute here. But first, I'd mention that I think Orientale actually has, of course, Mare Orientale, which offers potentially a smooth, low-slope area for a safe landing ellipse location in areas where we have targets of particular scientific interest nearby. So we can check that box off for Orientale. And then to get into some of these first-order mission concepts, I'm going to start with a lander here. in which we perform some short-term reconnaissance or perhaps long-term monitoring. On the right, I've identified just a few particular regions of interest where we might send these future landers. So we may want to investigate the smooth and rough facies of the Orientale Basin, the Maunder Formation, shown on the right. And on the left, there's actually a sort of unique location whereby some stratigraphy of this Maunder Formation may be revealed from this sort of polygonal plate of the Maunder Formation. Also, a possibility is to investigate a Maunder crater, which in principle samples the impact melt sheet of Orientale. And so
2 minutes.
Investigating the ejecta, thank you. Investigating the ejecta and the central peak would help us evaluate perhaps the composition of the Orientale impact melt sheet. So what possible surface actions that could be taken in these landed science missions include things like evaluating the physical properties, so something like the crystal sizes I mentioned earlier, investigating compositional characteristics and doing chemical analyses. Of course, doing radiometric age dating is important, as has been noted in several previous talks. And I think also very interestingly is the possibility to deploy in geophysical instrumentation, and in particular seismometers. Many of these instruments or measurements can be done with a rover mission, except now with the added benefit of the regional roving, so adding some spatial information. So we could do traverse analyses in terms of the chemical and compositional measurements as well as the geophysics. And then lastly, of course, sample return is always nice to have, in that we could perhaps provide much more precise constraints on the chemical and compositional aspects and the age dating. Ultimately, though, what is the yield, the scientific yield of these possible surface actions? Well, looking at the physical properties can provide information on the impact melt grain size distribution, which can help refine predictions on whether or not igneous differentiation occurred. Measurements of this and chemical and compositional information can allow us to evaluate peak shock pressure and evaluate siderophile abundances in the Maunder Formation materials. And this can help determine if indeed it was impact melt, because we would expect to see higher shock pressures and higher siderophile abundances in an impact melt versus the partially molten crustal material. Radiometric age dating, of course, would help constrain the age of formation of the Orientale Basin and its cooling history and help inform the broader stratigraphic chronology of the lunar far side. And then finally, the geophysical instrumentation and traverse geophysics can help us directly test models for the Orientale impact melt sheet through subsurface density images and structure analyses. So I'll conclude briefly by saying that Orientale is a compelling target for lunar landed science to investigate basin impact melt, with the potential of having safe landing sites from Mare Orientale. These important key questions about the nature of basin impact melt can be answered through these landed science missions to provide critical insights to the process of basin formation and for the geology and petrology of the moon as a whole. And these questions can be effectively addressed through lander and rover missions without necessarily having to do sample return, although of course that would augment the information that's provided by these potential missions. And so in summary, I would conclude by saying we can derive pretty significant scientific value through the investigation of impact melt through even short-term landed reconnaissance without requiring the more complex architecture of rover and sample return missions. So thank you for your attention, and I'll conclude.
Thank you very much, James. This paper is now open for questions or discussion. James, you may have tired this group out on Orientale.
Yeah, I was afraid of that.
Yeah. So what is, have you looked at, you mentioned Maunder Crater. How rough is that terrain? Is that something that you can rove over easily?
I haven't looked at it in any great detail, and it may be difficult to traverse across. I'm providing here just a list of potentially interesting targets that might help us address the real key fundamental questions regarding impact melt. So of course, any real landing site would need to be evaluated in more scrutiny before sending any actual missions.
I might just add to that we were actually considering sending an Apollo mission to the floor of the Copernicus crater right next to the central peaks. So, you know, I think it's certainly feasible.
Jack.
I just, in all of this discussion of getting samples of melt breccia, including the melt sheet material, you know, we got nice, coherent, good-looking, apparent melt breccias at Apollo 17, quite a number of samples. And we're still not sure about the relative ages of those, although I have a pretty good idea, I think, what they are. But getting agreement on that, and with error bars that approach 100 million years on each of the analyses, independent of isotopic system, I think, as was sort of hinted at earlier, we must get the geochronologists involved in this and see how in the world we get far more accurate and believable age dates of these melt breccias. They obviously are picking up, in some cases, in the old days at least, we're picking up information from the class that are in these melt breccias. I think we're getting much more precise in looking at the matrix and at what is probably the, much closer to the melt itself in these breccias. But still, we haven't resolved that. And I think it's important for the community to start to bring, as was suggested earlier, bring the geochronologists into this discussion and find out what our options are for improving this in the long term and in the short term.
James, do you have a comment or reply?
Yeah, well, I think, of course, enhancing our precision in terms of measuring the geochronology is always a worthy pursuit and should be something that we continue to attempt to do. But also, if we return impact melt samples from Orientale through some of these potential mission designs, having also the known and constrained geologic context, I think, might help greatly, inaccuracies of the geologic or radiometric dates aside.
Jack?
Well, that's exactly what we think we've been able to do in Taurus Littoral, but it is still, the dates themselves are not nearly as good as the geologic context. And that's, I think that's something that we're just going to have to keep working on and get more involvement and more urgent involvement of the geochronology community.
Okay.
I agree.
All right. Thank you, James. We're going to move on to our next presentation, which is by Dan Moriarty, which will be, a different basin. South Pole Aitken sample return insights from moon mineralogy mapper data. I'm not surprised, Dan.
So I do feel a little out of place in this session. I'm not talking about Orientale, and I'm not a former Jim Head student. He was on my committee, so I guess that counts. Okay, so I'm going to be talking about SPA. We talked a lot about SPA yesterday, so I'd like to return briefly as a detour. So insights into SPA from the Moon Mineralogy Mapper. So I don't think I need to figure out how to use this.
You want advance point it in that direction? Maybe?
Let's see. Nice title slide, right?
Ask Ricky to move it.
Could we advance? Or not? All right. So SPA, I don't need to convince the people in this room that it's a very pertinent science topic. It's essential to get sample return from SPA to address a number of really critical lunar science questions. So these questions address things like the basin formation chronology, the composition and stratigraphy of the lunar crust and mantle, large impact processes in general, the lunar formation and evolution of the far side, kind of specifically, and additionally, volcanism on the far side. So typically, when you think about SPA sample return, the kind of be-all and end-all of the samples we want to get are SPA impact melts, and that's definitely true. Those impact melts will help to address all of these questions. One of the things I want to emphasize in this talk is that we can actually gain a really unique perspective into some of these questions by looking at far-side volcanic products. And in this talk, I'll kind of identify some potentially unique volcanic products that may be localized entirely within SPA. So the primary analysis we're doing in this talk was through Moon Mineralogy Mapper. So our major goals were to identify and map the surface distribution of the critical sample types that exist within SPA that we want to return. We want to understand the compositional structure of the basin, and this offers kind of two advantages. So it helps us improve context for sample analysis, so when we get these samples, where did they come from and what do they mean? And also through these remote sensing analysis, we can also start to directly address some of these critical science questions that have been identified in the decadal surveys. So on the right, I'm showing a figure that kind of summarizes the M-cubed coverage of the SPA region. So the top right figure is the coverage across all optical periods of the M-cubed mission. And you see that the bottom 6 figures are coverage in different phases of the M-cubed mission. So we have coverage of different areas of SPA in different phases. There is some overlap, and that offers the advantage of being able to kind of verify what we're seeing in any given image. So M-cubed is a really complex and powerful data set. But in this talk, we're going to boil it down to 2 kind of essential spectral parameters, and these deal with pyroxene composition and abundance. So the first thing we're going to look at is the 2-micron absorption band depth, and this is sensitive to pyroxene abundance. So areas that are green, yellow, red, those are high pyroxene abundance. Areas that are blues and purples, those are lower pyroxene abundance. So what we see is that in the center of SPA, there's this kind of pervasive elevated pyroxene abundance throughout this whole zone. So we've called this the pyroxene-bearing zone of SPA. Outside of this zone is the heterogeneous annulus. This is mostly feldspathic, but it does exhibit localized mafic exposures. And then outside of the heterogeneous annulus is the SPA exterior, and that's mostly feldspathic in nature. So we can kind of continue to characterize SPA by looking at the second spectral parameter we'll look at today, and this is the 2-micron absorption band center. So absorption band centers are sensitive to pyroxene mineralogy and composition. So in general, short wavelength absorption bands show that there's very magnesium-rich pyroxenes. Longer wavelength absorption bands show that you have more iron and calcium-rich pyroxenes. So in this figure, things like orthopyroxenes, very magnesium-rich pyroxenes, would be showing up in blues. Things like Mare basalts that are very calcium and iron-rich pyroxenes would show up in red. So when we look at the pyroxene-bearing zone in the SPA interior, we see that we can actually break this down further into 2 very distinct zones. So most of the SPA interior exhibits very magnesium-rich pyroxenes, and these are findings that date all the way back to Clementine. This was observed then. One of the newer analyses that has come out in the last few years is that there's this central region of SPA that's somewhat compositionally anomalous. So this SPA compositional anomaly, or SPACA as we're calling it, exhibits slightly more iron and calcium-rich pyroxenes. So the difference is fairly distinctive between the SPACA and the magnesium pyroxene annulus throughout the rest of the SPA interior. So we can take this analysis a little bit deeper by looking specifically at impact craters. So impact craters are probes to the interior. The bigger an impact crater is, the deeper the material it digs up. And so we can look at crater structures, look at their composition, and get a sense of what's going on beneath the lunar surface. So let's start by looking at the magnesium pyroxene annulus. What we see here is that craters over a wide range of diameters are basically all exposing very magnesium-rich pyroxenes. And basically in this figure, what we've done is done a schematic overlay of the craters we've looked at. So the symbols that we've overlaid correspond to the 2-micron absorption band center. So again, blue symbols are more magnesium-rich pyroxenes, greens and yellows are more iron and calcium-rich pyroxenes. Any white symbols you see would correspond to a feldspathic, low mafic crater structure. So again, in the magnesium pyroxene annulus, over a wide variety of crater diameters and locations, we see fairly uniform exposures of magnesium pyroxenes. If we move out to the heterogeneous annulus, we see that actually most crater structures are fairly feldspathic. Where we do have localized mafic exposures, they're also fairly rich in magnesium-bearing pyroxenes. So when we put that together, we see that throughout the SPA interior, we have a kind of vast vertically thick deposit of magnesium pyroxene-bearing materials. The heterogeneous annulus exhibits the same mafic composition as the magnesium pyroxene annulus. And what that tells us is that these magnesium pyroxene-bearing materials were the primary material that were melted, excavated, and ejected during the formation of SPA. So the magnesium pyroxene annulus probably represents the SPA transient cavity, whereas the heterogeneous annulus represents SPA proximal ejecta that was ejected from the transient cavity and placed on the surrounding highland crust, and then further kind of mixed up during ejecta emplacement, the modification stage of the basin, and then subsequent impact cratering. And actually, impact models kind of do suggest that the entire extent of the SPA proximal ejecta may be constrained within the final topographic expression of the basin. So this wouldn't be much of a surprise. But basically what this is telling us is that the heterogeneous annulus is fairly complicated. Anything in there is going to be highly mixed up and kind of commuted with highland crustal material. If we want a sure sample of SPA impacts melt and breccia, probably our best bet is going to the magnesium pyroxene annulus. Okay, so we're going to move on and now talk about the SPA compositional anomaly, or SPACA. So again, we see that the surface composition is richer in these kind of iron and calcium-bearing pyroxenes, not quite as high calcium as Mare basalts, but somewhere in between the magnesium pyroxenes and the Mare basalts. We can kind of do the same thing as we did in the other areas and look at craters. So the crater we're going to specifically look at is Baba. So on the bottom right here, I'm showing kind of a close-up of the 2-micron absorption bands across Baba. You can see that in kind of the crater walls, floor, and ejecta. You see these green pixels, which represent kind of the SPACA surface material. But very distinctively, in the central peak, you can see these blue pixels. And this indicates that we have these magnesium-rich pyroxenes being exposed from depth. And so if you kind of put that together into a very simplified stratigraphy model, we can imagine that we have a superficial layer of this SPACA-type unit, which is higher in iron and calcium. That's a few kilometers thick, and that's underlain by this more magnesium pyroxene-bearing unit, which we see kind of throughout SPA. Okay. So that kind of local stratigraphy you see at Baba is mirrored across SPACA, so it's not just localized in this one location. The whole unit has a kind of similar stratigraphic relationship. So looking at the physical properties of SPACA, we see that it is fairly smooth and has a fairly low crater density. If we look at the Lola 20-kilometer crater survey, we see that indeed there is a lower crater density or crater population within the SPACA compared to the surrounding areas. I've also highlighted several of these craters in blue, and these are all craters that have been kind of heavily modified, either by embayment, burial, flooding, something like that. So in SPACA, we have a fairly low crater population, and the craters we do have all been kind of significantly modified. And so this really points to kind of a resurfacing origin for SPACA. So how might this resurfacing have occurred? One piece of evidence we can look at is mafic mound, which in a GRL paper from 2015 we noted is probably a kind of unique volcanic construct. It's similar to other magmatic constructs seen in other places on the moon. So what's interesting about mafic mound is that the mafic mound material is identical in composition to the material that's kind of spread across the SPACA surface. So compositionally, when we look at M-cubed data from SPACA, shown on these slides in green, the SPACA material is kind of intermediate, both in terms of albedo on the left and then the 1 and 2 micron band centers on the right, to the magnesium pyroxene-bearing materials, those are shown in blue, and then kind of your typical Mare basalts, both from SPA and the lunar near side, those are shown in red. So the fact that SPACA is intermediate to these two may at first suggest that maybe it's just a mixture. However, given kind of the vast extent of SPACA, about 700 kilometers, and the vertical thickness of several kilometers, maybe up to 5, it's hard to imagine a scenario where you can kind of homogeneously mix that much material to that depth over that extent just from magnesium pyroxenes and Mare basalts. So this may be suggesting that SPACA material is kind of a unique igneous product. We can get a little bit more insight of what's going on in SPACA by looking at the lunar thorium maps provided by Lunar Prospector. So although we do have thorium enrichments throughout SPA, mostly in the magnesium pyroxene annulus extending up into the heterogeneous annulus, there's actually a specific thorium low associated with SPACA. And so if SPACA is an igneous product, this has lots of implications for the magma source region, heat source, extent of melting, things like that. So to conclude, SPACA is an enigmatic 700-kilometer wide zone in central SPA, kind of as a reference point that's not so different from the size of Mare Tranquillitatis. SPACA is currently unsampled as far as we know. There's lots of evidence for resurfacing, so there's this paucity of impact craters, there's this kind of two-layer stratigraphy, and there's the presence of mafic mound, which is this interesting volcanic construct. So this kind of raises the question, could the kind of extreme geophysical environment of SPA have produced unusual mantle melts? So it's been discussed in the past, but things like localized mantle convection, extended pressure release melting, unusually long-lived impact melt solidification and differentiation, these are kind of all things that we have to be investigating and that are best investigated through sample return. So to wrap up, I think SPACA offers a really unique set of insights into the critical science questions that we can address with SPA sample return. And if we do go to a place within SPACA such as BABA, we know that BABA's definitively exposed these magnesium-rich pyroxenes that probably represent SPA impact melt. So it's possible to get both SPACA and SPA impact melt in a single landing site. And that's it. Thank you.
We have a minute and a half for questions.
I'm Makiko Otake from JAXA. Last year, we published a paper about substrate and in JGL. And in that paper, we interpret the central peak area as a product of differentiation of impact melt.
Right.
What is your interpretation?
So that's definitely a possibility, and that may play a role. I don't think it explains the physical properties of SPACA. So there's a lot of evidence for some pretty significant resurfacing, and you can't really do that just through impact melt differentiation. So you need some kind of later event basically to explain the lack of impact craters. The other interesting thing is that mafic mound, which is this volcanic construct, is the same composition as the SPACA material. So it's unclear if mafic mounds could have been produced by impact melt differentiation.
Okay, but how about this? At least you have two layers, so it's a product of Mare-like product.
Sorry, what was that?
At least there are two layers,
yes,
as you demonstrated. What is the origin for that?
Of the two layers?
Yeah,
right.
Blue and green one.
So that's kind of exactly what we're trying to figure out. So is it possible to have this several kilometer thick layer strictly by resurfacing, or does something like impact melt differentiation have to play a role?
Any further? Okay, thank you.
Thank you.
All right, that brings us to the last presentation of the session. This is going to be by Jennifer Whitten, exploring the volcanic and impact histories of the moon through analyses of material in Western Orientale. So Dan was the anomaly. Jennifer, are you with us?
Yeah, can you hear me?
Yes, the floor is yours.
Excellent, thank you, David. So I'm bringing it back to Orientale and kind of bookending this session by talking about a site in Western Orientale that I think would be really interesting to explore a little bit further, and that would be a really straightforward mission concept. You've heard the background about Orientale in a lot of detail, and I'll only highlight some points here. But I want to make the point that Orientale is uniquely situated on the near-side, far-side boundary of the moon, and that enables measurement potentially of some far-side materials and materials that are outside of the Persolarum Creek terrain. As Jim and other people have mentioned, Mare basalts within Orientale span a large age range, and that's based on some crater model ages. that I studied a couple years ago. And those ages span almost 2 billion years of time, and as Debra pointed out, they are older in the center of the basin and then get progressively younger as you go radially away from the center of the basin. And then there's a lot of interesting depositional environments within the basin, and what I mean by that is you have the central deposit of Mare Orientale, but you also have Mare ponds between all of the different rings, so between the inner and the outer rook, between the outer rook, the Cordillera. And there are about 24 different Mare ponds. Here's an image highlighting exactly where they are, but what's really interesting is that the Mare ponds reflect this near side, far side dichotomy that's observed in Orientale, where the most aerially extensive and more numerous deposits of Mare basalts are found on the eastern side of the basin, and the smaller and less numerous Mare basalts are found on the western side of the basin. And I'll be talking about one particular Mare pond on the western side of the basin. Here's a figure showing the region that Debra talked about earlier on the eastern side of the basin, and I'll be focusing in on this area with the bolded rectangle here. But this site has been chosen for one really specific reason, and that's the proximity of a variety of geologic units to one another, and that includes Mare basalt, the Orientale basin melt sheets, the Mondor Formation, and basin ring materials. So those are really the three things that we're going to try and sample to address some fundamental questions that a variety of people have brought up already today. Here's a close-up view of the proposed landing site. This is the Mare basalt deposit outlined in black in the left-hand side. This is some Lola topography showing just how flat the deposit is. In the bottom left of this particular Mare basalt unit, there is a massif from the outer rook ring, and then you also have the eastern side of this unit, or the eastern side of the Mare basalt being bordered by the Mondor Formation. On the right-hand side of this slide, I'm showing the M-cubed mafic color composite. So what should stand out is the mafic minerals that are shown in the yellow tones. This is the standard 1 micron integrated band depth in the red channel, the 2 micron integrated band depth in the green channel, and then reflectance at 1489 nanometers in the blue channel. But what's really interesting, and what you can really tell in the M-cube data, is that you also get some other interesting mineralogies that appear in the outer rook ring area over here in the bottom left. I don't know if this cursor is working. There we go. You can see the change in color here. It's a little bit lighter blue to white. And then over here on the eastern side of this Mare basalt deposit, you have more pink tones, and you get more of an orthopyroxene signature associated with these particular deposits. The site circles are those areas that I'm particularly interested in, and I'll present traverses through to these different sites. Next slide here. So on the left, I'm showing one proposed means of going about analyzing these particular sites, but you could just as easily go 3, 2, 1 as 1, 2, 3, or 2, 1, 3. But what I want to show here is that it's sort of my ideal traverse. If I could have all of the roving time and all of the instruments, these are the particular sites that I would go visit. And then over on the right, I'm showing a slope map derived from the LRO Lola DEM. And what you can see is that for the most part, these slopes are 1 to 2 degrees. There's not a lot of variation within this Mare pond. And it's only when you start approaching the various sample sites that you're reaching high slopes. For example, you might reach slopes of 10 degrees at the Site 2 location. At Sites 1 and 3, you're reaching slopes between 20 and 25 degrees if you're getting really close to either the massif or the crater rim. The science goals are very similar to other science goals that have been presented by previous speakers, and that includes constraining the bombardment history of the inner solar system by measuring the age of the Mondor Formation impact melt, characterizing the diversity of lunar rocks, which we would be doing by measuring these different, 3 different units, looking at investigating volcanic materials and how they constrain the thermal and compositional evolution of the moon. I think studying this particular Mare basalt pond that's more situated in a far side environment would be very useful and contribute to our understanding of how these types of basalts are in place. And understanding regolith processes in weathering by measuring the composition of regolith across different sample sites and as well as between sample sites. This Mare basalt pond, take a step back real quick, you can see in the M-cube data, and I don't know if you remember, but from Debra's presentation, the M-cube data there, you didn't even see this particular Mare pond in the lower resolution data. Here you can see it only because of all the small impacts that are occurring within it that are appearing yellow in this diagram. But it has more mixed regolith than other Mare basalt ponds. And I think it'd be really interesting to be exploring the regolith composition at each of the landing sites, and then as you move progressively away from the various boundaries between the outer Rook and the Mare, and then from the Mare to the Maunder Formation. So I think there's a lot of really great science that could be accomplished by going through these different sample sites or similar sample sites. Here's a close-up of the first sample site. This is at the base of the Maunder Formation, or of the outer Rook ring here. This is a massif that I'm showing right here. Here's the boundary between the massif and the Mare basalt. And what I really want to point out is this field of boulders that appear to be sourced from this outcrop further upslope in this massif. Looking at M-cube data, it appears that you get a strong anorthosite, sort of pyroxene, not pyroxene, plagioclase absorption feature when looking at these features in M-cube. Leah Sheikh did a really comprehensive study of anorthosite throughout Orientale, and this particular area around the sample site, but in the southwest part of the sample site, you get both the pan, the 98%, and the sort of less than 95% plagioclase within the material. So there's a diversity of materials potentially within this area to investigate. And zooming in a little bit further, you can see there's a lot of boulders and a lot of rocks that are available to us here that could be good for sampling. The second sample site is right at the boundary of the Maunder Formation and the Mare basalt. I'm proposing to look at two crater rims potentially along the western or southwestern edge here, or along this rim of this crater here. They have the nice orthopyroxene. Thank you. Nice orthopyroxene absorption feature, and I think sampling boulders in either of these areas, which generally reach slopes of around 10 to 15 degrees, so they'd probably be accessible via rover, would be feasible. And the last sample set, oh, and there's a close-up view, so you can, and believe me, there's plenty of boulders along each of the rims here that we could sample. And lastly, the third sample site, which is Mare basalt, and this is sort of my ultimate, if I could go to any of the impact craters within this deposit, I'd want to go to this one in particular. It's relatively fresh. It has a really strong spectral absorption feature, and there's a lot of boulders right along its southern rim and just on the exterior part of the rim. So they're much more reachable by rover than other boulders that are closer to its interior. And I want to propose just two quick alternate traverses. I understand that 35 kilometers is a really large distance. The Lunar 2 did it in less than 5 months in 1973, so it's not an unrealistic distance, but I understand that that's pretty far. So there are two other impact craters, or regions of impact craters that we could potentially study, this area B and C, that have fewer boulders. They're a little bit more mature craters, and so it may be difficult. There wouldn't be as many boulders to sample here, but they all have nice basaltic absorption features as shown in the M-cube data. And then I just want to briefly go over potential instruments. This is, again, sort of a wish list, kind of having an arm with a rock abrasion tool or some sort of tool to clear off the surfaces of the sample so that we could measure the interior of the sample rock would be ideal. For compositional analyses, having something like XRD and XRF so that we can measure both elemental composition and then get some information crystallographic information about the mineral structures, I think would be really important. High on my wish list would be a Veneer spectrometer. I think you could quickly characterize the mineralogy of a terrain and then select different samples using an instrument like this. And it would also be useful for ground truth for orbital data sets that we already have in our possession. Again, having high-resolution cameras for navigation and also sort of a micro-imager, in addition to having an instrument similar to the Carly one that Noah talked about, date these materials in some way. So to summarize, I think sending a rover mission to the western edge of Orientale would, to conduct in situ analyses at 3 sample sites would produce very fruitful results. We'd learn a lot and supplement what we've already learned from the lunar near side. And with that, I'll leave you with the summary of sort of a science traceability matrix style table. Thank you.
Perfect timing. Thank you very much. Jennifer's paper is open for questions, discussion. Noah looks like he has a burning thought.
I fell into a ring of fire. I have a question really for all the Orientale presenters. And this is something, in talking quickly with Ben as we start talking about more far side missions and Orientale straddles that, is Jenny, since you're on the mic now, have you done any communications evaluation, direct line of sight to Earth? Orientale's in a tricky spot because sometimes, so have you guys looked into that at all?
I have not, so as I was putting this together, I thought about that, and so it's something I'd like to look into further. I don't know if anybody else who's looked at Orientale has looked at it.
We can add something from Brown. Are we on okay?
Yeah.
Okay, so clearly, as Carly has pointed out, infrastructure for communications is critical. I think, we're not going to do any of this, particularly any of the kind of thing that we're talking about here with the Orientale architecture without a communications infrastructure. And frankly, I think that the person who has the infrastructure for is really going to be the one that controls the situation. So I hope that the United States steps up to putting an infrastructure in orbit to help all these different missions, from commercial to, in fact, international missions, to provide the capability to, in fact, execute them, because it's such a basic thing. I mean, years ago, everybody went to the West and covered wagons. They took everything with them that they needed or had, and, we're beyond that. And we do that with space missions. They're all independent. We should put the infrastructure in place for communications and other types of things, and then, we don't have to do that. It would be really great. So I think that's a fundamental part of the future that commercial entities could actually implement and actually maybe even have a good business plan for that. Thanks.
Okay, so Jack, I'll get to you in just a minute. So for those of you online, we're now going to switch to our panel mode. We have about 7 minutes for general discussion with all of the speakers. So those of you who have questions, you can address them to any of the session's speakers. Jack?
Yes, I was just going to add to that last discussion that after Apollo 13, an informal group, the Lunar Mafia down at Houston, got together and felt like to rejuvenate the program that the last 4 landings should be in places that everybody always wanted to go, and Orientale was one of those places at that time. And we did look at, as I recall, at the communication issue, and the western site has a problem in the extreme libration of the moon. So, but timing with respect to lunar libration certainly might well solve that problem. For most of the traverse that I saw, I'm not absolutely sure. That would have to be looked at in detail.
Yeah, no, my memory is exactly the same, that you can actually communicate just beyond the limb, depending on where you are in the libration. Also, he's not here, but Alan Stern had done a study a little while ago that said that for things right on the limb, and he was thinking of Orientale at that time, you actually could relay through an Earth-orbiting comm satellite, but it just buys you just a little bit beyond the limb. Yeah, I think Brian was up first, so go ahead, and then we'll come back.
Okay. Going back to the Western Orientale site, I noticed that your northernmost site, the crater that you had indicated, in addition to being relatively fresh looking and having exposed boulders, also really stands out in WAC imagery for a very prominent dark halo that is pretty much unique in that area. Is that of particularly interest to you, and what is your interpretation?
Yes, that is very interesting to me. I think I was sort of hinting at it a little bit, but the salts are very low, high albedo for this particular Mare pond. I think there's probably a thin veneer of some ejecta covering, maybe from Lowell Crater, which is just north of it. And so that's kind of obscuring the lower albedo of the basalt. And what you're getting with this relatively immature impact crater is it's excavating through that thin layer, that thin veneer of ejecta, and exposing the underlying basalt. And you're just seeing it really nicely here because it's relatively young.
Okay.
But I think that would be a really interesting place for regolith studies in this particular area as well, because if most of the area is covered with ejecta from adjacent craters, then that would be one place where you're going to get a good study of basaltic regolith.
David?
My question was for Debra. What was the length of your traverse over there in Lacus Veris?
Yeah, it was just over, well, just under 20 kilometers total.
So I have a question for anybody who is speaking about rovers. Do you have any favorite speed for your rover?
Well, 20 kilometers, unless we're going to last multiple lunar days, we're going to have to go pretty quick to get it in 2 weeks. But no, but realistically, we will have to operate over several lunar days, I would say.
Jim, Jennifer?
I would echo what Debra was saying, that I'd love to be able to zoom around, but especially with my kind of ideal 35-kilometer long traverse, I don't anticipate being able to cover that and do science kind of along the way in one lunar day.
Jim?
So I'd add to that so with this MIT study we've been doing, I think we have a paper in AIAA somewhere. I'll try to get it and send it around. So we did a little kind of a campsite option where that you carry on the back of the rover a module which you can construct to like a tent. Okay, so you can actually during a normal Earth day, as part of a longer traverse, bed down for a period of time and rest, and then press on from that. So I think there's lots of different options for extending the length of these traverses up to tens of kilometers.
Yes.
Yeah, I want to ask.
Can you lower the microphones to the?
Okay.
Yeah,
Okay.
there you go.
Yeah, yeah. I want to ask everyone, the speakers, and anyone want to run on the relatively sloped area in your candidate site? I mean, because as Junichi introduced yesterday, we Japan are planning to go on the moon by tipping off type of the landing module. Is that, I want to ask, if is that technology somehow help you run on the sloped area or not?
Think about that. I mean, certainly, yeah, I think getting there at all would be great. It depends, of course, on how you put the instruments in the tipped over part, because we definitely want to be able to well, at least the instruments that we were proposing, we want to transfer samples onto an instrument deck to be able to use an SCM or a XRD XRF. But an XRF needs contact, so that is an instrument example that you could use in the tip over motion to get direct access to the surface and get some of the data that we want.
Thank you.
Dan?
So one of the nice things about SPACA is that it's a fairly homogeneous composition over 700 kilometers or so. So pick a slope and have it within that terrain. That's as long as you don't also want to get SPA impact melt samples. That restricts you quite a bit to more geologically rough terrains.
Jim, did you have a comment about the tip over?
I think there's a person behind Makiko that could probably answer that better. But as he said earlier, both on Apollo 15 at Heavy Delta and also at Jack's landing site, you just have to learn how to navigate. You can actually do some of these slopes. Dave Scott even said, gee, looking over, we probably might have been able to get down into the rill. That was like, in excess of 12 degrees.
Okay.
Jennifer?
Yeah, I would just say that I did a little bit of looking up, and so Curiosity has navigated slopes up to 30 degrees, so possible.
Okay.
There's plenty of areas that I would like to look at, yeah.
Thank you.
All right, yeah. We got two issues confused, but we're okay. So final comment with Jack, and then we're going to...
It's sort of a center of gravity issue, and if you manipulate that, and you can do pretty good slopes. On the, Noah and I were talking at noon a little bit about that with this vast database we're gathering and have gathered with LRO and LROC, I think we need to take a step back and think about new navigational techniques that allow you to plan and to implement an automated traverse with the ability to intervene if the guidance camera, look-ahead camera, says that you're getting yourself into trouble. I think you can speed up these traverses with this database. If we can't use this database to speed up traverses, then then we've wasted some of its value. So I would just suggest at some point the appropriate people get together and think about that operationally, so that you're not in a Mars mindset. That you actually initiate a traverse and then stop it if you have to. We can do that on the moon. You can't do that on Mars, but you can do that on the moon, and you have the database to do it.
And you're speaking of the robotic rover?
Yes, a robotic rover.
All right. Yeah.
No, a human rover, that's no problem at all.
Yeah, the human rovers, they're hoping to do up to 20 kilometers per hour, which is pretty good.
No, I don't think so. Not in 1/6 gravity.
No.
We did 18, and that was a little bit fast.
No, yeah, but they were aware of the LRV problems, so they have independent transmission wheels that hug the ground. All right, I think we have to move on. I know Brad is anxious to get to the lightning rounds. Before I turn this over to Brad, I want to thank very much the people behind the curtain back there who are handling 3 external talks flawlessly.